3I/Atlas, recognized as only the third confirmed object from interstellar space to enter our solar system, has captured global scientific attention due to the rarity and mystery surrounding such visitors. Unlike the countless comets born within our own solar system, interstellar objects originate from distant star systems far beyond the gravitational reach of our Sun. Their trajectories, compositions, and histories are shaped by cosmic environments entirely different from our own, making their brief appearances extraordinarily valuable for astronomers. When 3I/Atlas made its closest approach to the Sun on October 29, 2025, at precisely 11:47 Universal Time Coordinated, the object came within approximately 1/36 astronomical units of our star. This translates to roughly 126 million miles, or about 203 million kilometers. Although that distance is far greater than typical perihelion distances for many comets from the Oort cloud or Kuiper belt, it is still significant because it marks the moment when the Sun's intense heat and radiation most strongly influence the object, triggering outgassing, tail formation, and other features essential for scientific study. As an interstellar comet, 3I/Atlas carries with it the chemical fingerprints of its home star system, offering clues about how planetary systems form elsewhere in the galaxy. Its hyperbolic orbit clearly shows that it is not gravitationally bound to the Sun and will not return once it leaves. Currently, after rounding the Sun, it is traveling outward again, continuing on its escape trajectory. Even though it has already passed the point of closest approach to the Sun, it has not yet reached its closest approach to Earth. That encounter will occur around December 19, 2025, when it will pass at a distance of roughly 1/8 astronomical units, or about 168 million miles, 270 million kilometers, from our planet. Even at this closest point, the comet will remain relatively far away, too distant to become a prominent spectacle in the night sky. Because of its extreme distance, dimness, and the effects of solar glare, 3I/Atlas is currently extremely challenging to observe. From Earth's perspective, the comet is presently moving through the sky very close to the Sun. This means it is hidden within the daytime glare and cannot be seen using normal observational techniques. Only highly skilled astrophotographers, using specialized equipment and perfect timing, have succeeded in capturing faint images of the comet so far. Their success relies on photographing the sky during the brief period just before dawn, a moment when the comet rises slightly ahead of the Sun and becomes barely visible before morning light overpowers it. Even so, these attempts demand long exposures, precise tracking, and extremely sensitive imaging systems. Casual sky watchers or amateur telescope users will not be able to locate the comet at this stage. As the weeks progress, visibility is expected to improve slightly. Observers equipped with at least an 8-inch (20 centimeter) telescope may have an opportunity to spot 3I/Atlas in late November, when its position in the sky offers a brief observational window during the pre-dawn hours. Even then, the comet will appear extremely faint, likely as a diffuse smudge of light rather than a well-defined object. It will never become bright enough to be seen with the unaided eye. Its lack of naked-eye visibility is not surprising, considering its distance and relatively modest size compared to well-known comets like Hale-Bopp or Neowise. Despite these limitations for ground-based observers, one spacecraft will have an exceptional vantage point. Between November 2nd and November 25th, the European Space Agency's Jupiter Icy Moons Explorer JUICE mission will conduct scientific observations of 3I/Atlas using a suite of advanced instruments. Although JUICE was launched primarily to study Jupiter's moons, including Europa, Ganymede, and Callisto, the spacecraft is well equipped to investigate other targets when mission timing and geometry allow. During this observational period, JUICE will be in a position that offers a clearer, unobstructed line of sight to the comet. Because the spacecraft orbits far from Earth's line of glare and atmospheric distortions, its instruments can capture fine details of the comet's coma, nucleus, dust tail, and gas emissions that would be impossible to detect from the ground. This timing is especially important scientifically, because the comet will still be highly active after its close approach to the Sun. When comets approach the inner solar system, solar heating vaporizes ices beneath their surfaces, releasing jets of gas and dust. This creates the glowing halo known as the coma and forms the tail that streams away from the nucleus. For 3I/Atlas, this moment provides a window into its chemical composition, including volatile substances that may differ from or resemble comets in our own solar system. Interstellar comets can contain exotic mixtures of frozen hydrocarbons, carbon monoxide, water ice, crystalline silicates, and other materials shaped by the environment in which they formed. Identifying these components allows scientists to compare planetary formation processes across different star systems. JUICE's instruments, including spectrometers, imagers, and particle detectors, will examine the comet from multiple angles. These tools can measure temperature variations on the nucleus, analyze dust particles, detect ions created by the interaction of solar radiation with the comet's gases, and record changes in brightness or structure over time. The long tail of 3I/Atlas, illuminated by sunlight streaming past its nucleus, will also be imaged to determine how dust grains scatter light. Studying the shape and brightness of the tail can reveal the size distribution of dust particles, the speed at which they are being ejected, and the influence of the solar wind on their motion. The scientific community is eagerly awaiting the data from this observational campaign, but the JUICE team does not expect to receive or process the collected information until February 2026. This delay is normal for deep space missions, which must manage slow data transmission speeds, complex calibration procedures, and detailed post-processing before final results can be released. Once the data arrives, scientists hope to answer fundamental questions about the comet's origin, structure, and evolutionary history. For example, they may determine whether the comet formed close to or far from its original star, whether its ices have been partially processed by cosmic radiation during its interstellar journey, or whether it has undergone significant heating events before entering our solar system. Interstellar objects typically travel for millions, or even billions, of years through the galaxy after being ejected by gravitational interactions in their home systems. Their surfaces become weathered by radiation, micrometeoroid impacts, and freeze-thaw cycles in interstellar space. By studying 3I/Atlas, scientists can gain a deeper understanding of these long-term processes. The discovery of 3I/Atlas also adds to our growing catalog of interstellar visitors. Following the groundbreaking detections of 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Each of these objects presented unique characteristics. Oumuamua exhibited no visible coma and displayed unusual acceleration, leading to ongoing debates about its shape and composition. Borisov, in contrast, behaved much more like a typical comet, with a healthy coma and tail. 3I/Atlas appears to align more closely with Borisov in terms of behavior, with clear signs of cometary activity. However, every interstellar object offers distinct clues that help refine theoretical models about how objects are formed and expelled from star systems. Some may have been thrown out during the early stages of planetary formation, while others may have been gravitationally kicked out later by massive planets or close stellar encounters. As astronomers prepare for the brief observational window from Earth, many enthusiasts anticipate organizing pre-dawn gatherings to attempt a glimpse of the comet through telescopes. These so-called star parties, while unlikely to reveal a spectacular naked-eye display, offer participants a rare opportunity to witness an object that originated from another part of the galaxy. Simply observing 3I/Atlas, even as a faint, barely perceptible glow, connects viewers to the broader cosmic environment beyond our solar system. For many people, the idea of seeing something that has traveled across interstellar space for potentially millions of years is awe-inspiring and humbling. Although 3I/Atlas will not become a bright comet or leave a visible mark on the sky for the general public, its scientific importance cannot be overstated. Every interstellar visitor gives astronomers a new data point, helping refine our understanding of the diversity of materials and processes in the universe. Unlike typical periodic comets, which follow predictable orbits and return after set intervals, Interstellar comets are one-time visitors. Their appearance is fleeting, and once they leave the solar system, they will not return. This rarity places enormous value on each opportunity to study them, making missions like JUICE's observations especially significant. In the end, the brief passage of 3I/Atlas through our solar system is a reminder of the dynamic and interconnected nature of the galaxy. Star systems are not isolated. They exchange material over immense timescales through ejections, collisions, and gravitational interactions. Objects like 3I/Atlas bear silent testimony to events that happened long before humans existed, carrying with them records of distant cosmic histories. Whether viewed faintly through a telescope or studied in exquisite detail by a spacecraft millions of miles away, the comet offers a momentary glimpse into the wider galactic neighborhood and deepens our understanding of the universe we inhabit.